needs that? Okay, ladies and gentlemen, I never need a microphone in any class. So what we are doing here, maybe before they are started, it is for some of the visitors, we are describing what we are doing, right? You have seen a mission, and they designed an airplane with a fuselage and a wing which is changing sweep angle. Actually, we are coming from industry, from Airbus industry, that's exactly happening there. That happened at the time there. The second team right now has the identical mission, but they are changing for a different configuration. It doesn't have a fuselage, it's just a wing, called the flying wing. So what we are doing here is, these two teams have the identical mission, then they're producing a product. At the end, both teams are trying sort of to come together, compare which design may have a better promise of surviving, of providing performance, of lower cost. Remember, cost plays a role. I heard that just before, right? By the way, note down equations. Sorry, not equations, questions. Write down, don't ask for equations that much. Write down your questions, everybody. So, because what we will do then after the finalizing here of this team, whenever they have compared, we are waiting for your questions. Then, of course, after all of these questions from the audience, maybe my teaching assistants, we are providing some questions too, but we may hold back a little bit. And then we are launching both teams. One team here, second team here. Those guys are starting to question their product because it's done competitive. They don't really know what the competition is doing overall. But you have to imagine if this would be Boeing, and Boeing would design this, they have a red team and the blue team, they are not together, of course, and they would identify at the end which one is the winning design along these lines. So, having said this, good luck with the microphone. Thank you so much.
Yes, Chief. Yeah, having some technical difficulties over here. All right. My apologies.
All is good.
Thank you, whoever that was. Is everybody ready? All right, good evening. My name is Jacob Navarro. I'm the Chief Engineer of Falcon-X Aerospace. We're here in front of you today to present our Senior Design 2 project, conceptual design of an oblique flying wing supersonic transport. Oh my gosh, okay. So our mission is to lead the way in shaping the next generation of aerospace technologies, fueling progress and unlocking the limitless potential of humanity for generations to come. Shown here is just kind of a picture of our team. I just want to introduce our team members real quick. Right here I have my geometry lead, Tyler Jones, synthesis and geometry member, Jared Calderon, civilian control and propulsion member, Andy Morales, propulsion lead, Adam Concha, weights and balances lead, Prince, weights and balances and civilian control, Oscar, trajectory and performance lead, Daniel Hernandez. That's Daniel, there we go. Aerodynamics lead, Nicholas White. Weights and balances and trajectory and performance member, Dennis. Stability lead, Arnold. And then we have trajectory and performance and cost member, James over there. So one area of emphasis we place as a company is on honesty. We try to let the numbers speak for themselves rather than the other way around, meaning we know we're dealing with a pretty unconventional configuration. So at the end of the day, whatever the results tell us is what we interpret. We also care about accessibility, striving to produce products that everyday people can use. Here's just a team breakdown. One thing we really care about is communication and documentation. And we're just trying to show here that we meet a lot, we talk a lot, we stay on top of it. So moving on, we go to initiate this project first by defining our objective, and that's to conceptually design an asymmetrical all-wing supersonic transport that can complete and compete the boom overture mission requirements shown here. The purpose is to generate a comparison between these three types of vehicles you see here and determine which is the most viable, assuming a market and technology level reflective of today's current industry. Here you have the Boom Overture, which is a traditional tail-aft vehicle. Here is our concept, the oblique all-wing, and here is the previous team's concept, the oblique tail-aft vehicle. Now these two vehicles are asymmetric, and I'll explain that here in a second. So why do we care about asymmetric configurations in the first place? The answer to that begins with a very brief review of human history. We weren't always able to fly. Eventually we got there, thankfully, but it was a long journey. As you can see, we kind of go from being jealous of the birds, to getting off the ground, to breaking the sound barrier. Eventually, flight becomes commercial. Now, it becomes commercial subsonic first, but after around 20 years of development, the Concorde comes about. 2003, the Concorde retires, and with it, supersonic transports disappear from the market. The fact is, though, humans are impatient and we want to get from point A to point B as fast as possible. So if that's the case, why have subsonic wide-body jets seen 45 years of continued success while we've seen 30 years of no supersonic civil transport? The answer to that's a little complicated. It lies in how the physics behind the wing, engines, control surface, and structure interact. These physics are leveraged in those configurations favored to produce a scenario where performance is optimized. That helps us win by getting quick travel at an affordable rate, but it could be quicker. We can compare two classic examples here, the A380 and the Concorde. Just focusing on some of the main stuff here and not everything is the lift, like the lifting body and the wing shape. So here you get a large aspect ratio with swept and tapered wings to provide the best aerodynamic efficiency at a subsonic speed. But for the Concorde, you get a much smaller aspect ratio. The Concorde, and it kind of mentions this here, the supersonic configurations to maintain somewhat of a close level of efficiency, they have to manage the compromise between supersonic and subsonic regimes. The Concorde poorly lacks in subsonic performance, which is one of the reasons it was canceled, but not all of the reasons. A lot of those reasons can be summarized here. I'm not going to go through all of these, but it's clear the design problems associated with supersonic transports aren't just the trade-off between low speed and high speed efficiency. It's how all of these items here interact to limit the economic feasibility. The Concorde itself was never profitable, but that ended in 2003, right? So in more recent years, you have these companies like Boom, Ariane Supersonic, and Spike Aerospace emerging with their own supersonic commercial products, which are summarized here. Now, these configurations aren't identical. You can see some differences in packs count, but what's really important is the timeline. No matter what supersonic commercial vehicle you look at, the timeline either gets shut down completely or dramatically extended. And then when the deadline comes, it gets extended again. And the deadline comes and again, and it becomes clear. If you take a similar approach, you get similar results. So how do we break the cycle? We break the cycle by asking ourselves, what configuration changes could be made to increase the economic feasibility? We can kind of break that down into three simple aspects. Aerodynamics. If we can dream up a supersonic configuration that maintains subsonic performance, we can get back some of that performance, reduce the operational cost, and thus the ticket cost. Propulsion. The engines on the Concorde were really noisy and really bad for the environment, so moving forward we have to mitigate that issue as well. And then payload capacity. The Concorde was very skinny and cramped. You can see that on this image here. And that was because it has to maintain a very slender shape to get that performance even at supersonic. So again, we asked ourselves, why do we care about these configurations? So kind of what the other group is working with, it's clear having this asymmetry, and shown here, gives you the optimized L over D across all speed regimes, gives you a lighter and less complex wing. These all function to lower the operating cost, but when we think about our configuration, what do we add? We get increased payload and structural efficiency, meaning we can try to imagine a scenario where we have more passengers. The Concorde had about 100. We're personally trying to shoot for around 300. And we integrate the volume and lift simultaneously, which allows us to fit more payload. To initiate this design, we should collect literature to break the functionality, of the vehicle into 4 main components shown here. In this process, we analyze a lot of old OAW, oblique all-wing designs. These aren't the only ones we consider, but there's some of the major few. So this literature review process should be organized and communicated so each discipline can produce useful output along these lines here. And we'll move into some of that disciplinary output now. I'll point for you. Okay.
So trajectory and performance supplies a baseline trajectory, and this not only ensures that all flight phases are considered in our analysis, but it also dictates the flight conditions at which those analyses are performed. So in our considerations, we consider the mission purpose, which gives us horizontal takeoff and landing. We consider the mission requirements, which gives us cruise, Mach, and altitude. And we also take FAR regulations into consideration. So for example, sonic booms are banned over land, so that forces us to have our deceleration and descent phase 180 nautical miles away from shore.
So the focus for stability and control is obviously selecting the control vectors we're going to use to move forward. Some of the most important considerations are the strong coupling between pitch, roll, and yaw, and then the fact that we have a Telus aircraft on our hands. As you can see here, this is the aircraft we have considered, and this is our layout for the control vector.
So propulsion's primary objective in project initiation is to conduct a comparative analysis of the feasible engines, such as the turbojet and turbofan engines. So through that, we wanted to do a literature search of these all these vehicles here, these engines, and also the inputs of synthesis and the compliance regulation of noise. Next slide, please. So through this analysis, we determined that the turbofan engine would be better performing for the noise mitigation compared to vehicles such as the Concorde. And that way we have that's due to the bypass ratio here, that's larger than, that has a bypass ratio compared to the turbojet. And then turbofan would be performing similarly to turbojet, so that's why we consider that, as well as to meet the boom symphony.
The oblique all-wing comes with inherent problems with the design, but like the concept, and we want to be able to fix those on the front end rather than the back. So everything that we send through is going to be feasible past at least configuration, initiation, layout, and then hopefully evaluation continue.
Okay, so to perform any sizing process, we need to have an understanding of the way the vehicle scales. If you want a larger vehicle, does it get larger photographically? Does the thickness get larger? How does its volume scale? But as you may have noticed, you don't see any of these vehicles flying around. So what we had to do to determine those relationships is we created a database of 200 vehicles that we iterated through all of the feasible iterations of span, thickness, taper ratio for the possible configurations that fit on a runway that we thought we could reasonably build. From those, we scripted through VSP, it just generated based on a first baseline parametric model, spit out 200. We trend fit those for tau as a function, our KW as a function of tau, and that gives us a scaling law that we can use in the sizing methodology to size up or down our vehicle. And on the right here is a more detailed view of the step-by-step process that we did to determine those relationships. And the things we found there were kind of interesting. The KW doesn't have a wide range as it sometimes does with other configuration types. It's pretty stable at around 2 to 2.2. But that gives us good confidence in the fit of the equations that scale the vehicle that we feed into the sizing logic.
So, talking about sizing, the next step in initiating this project is for synthesis to find a clear, detailed, and thorough methodology. Now, sizing is the first step, and then we move to configuration layout and configuration evaluation. Here we generate the area, weight, and volume budgets of the vehicle. We then allot to the individual components, both internally and externally. And then we move to the evaluation phase to analyze the physical feasibility, meaning can it meet the mission requirements, and the economic feasibility, meaning is it profitable. This is just a rough overview of the methodology followed. Not going to spend much time here, but just to show it is thought out and organized. And these are some of the deliverables we have to meet. Mainly focusing on, we plan to produce 2 OAW designs, the 80 pack, for comparison of what we identify as the best case passenger count. So when we move from initiation to sizing, our objective is to determine the optimal size, if one exists, for the given mission criteria. Meaning, do we have a solution that meets performance constraints at a reproducible size? We reviewed a lot of literature to determine what kind of scheme we wanted to solve. We picked hypersonic convergence because of its ability to converge on a weight, volume, and area budget simultaneously. And it does so through this parameter called tau and a multidisciplinary set of equations. So brief explanation of tau. It's shown here. Basically, as you increase your tau, you get more stout. And these are the multidisciplinary set of equations that wrap up output from geometry, weights and balances, propulsion and trajectory and performance, along with tau that you solve for to get the size and budgets of your vehicle.
So from the convergence, you have multiple parameters that you're iterating over, so you're going to have hundreds of results. Well, hundreds of points on the space. So we're going to need to limit those. First stat's going to be the landing length required, so which runways do you actually want to land at? So we want Heathrow. Next is marketability. We want to be able to compete with Motor. Next, volume efficiency. So we want to have the maximum amount of passengers for the minimum amount of volume. And then insights into aerodynamic performance, just anything that made it through the selection, we're now saying which one performs best.
So for propulsion and parametric sizing, the methodology was approached using the ideal parametric cycle analysis, and this was used to determine the engine parameters that would be initializing the power plant of the vehicle. And the literature would be used the elements of propulsion by Mattingly and the mission requirements, and would come as the inputs to that methodology. Excellent. So here are the verification results for the ideal PCA analysis. This is from Mattingly's Para software, and the analysis was done using MATLAB programming that I developed. Next slide, please. And these are the outputs of the result of that analysis, where this is where our component sizing comes into play for later on in configuration evaluation when we get to engine performance analysis.
Great. So trajectory performance performs a constraint analysis, and this is to ensure that the thrust requirement is met for all flight phases. And so our method was verified within 9% of Concord data. And so this is the reason we do this. So the transonic acceleration phase was initially assumed to be at 60,000 feet right before cruise. That purple line up there shows us that the thrust we would need is very high. So we bumped it down to 30,000 feet, and after verifying that we did have enough thrust for that phase, this is our new trajectory with a new supersonic climb setting.
Part of the responsibility of the trajectory and performance team is to generate a trajectory analysis. In here we generate the fuel fractions that the aircraft will be able to fly in the mission, and that will help in sizing the aircraft, in determining the maximum range that it can achieve, and it's incorporated into the sizing code. And some of the those are some of the fuel fraction values for common civilian aircrafts. Next slide, please. And for our design, these are the fuel fractions that developed from historical data and the methodology as applied. So for this one, this will be for the 80 passenger and the 300 passenger designs that will be explained later in the project.
Now for weights and balance, excuse me. Their main objective is to determine different weight components and weight coefficients to be used in this weight budget, right? We'll be using a couple different methodologies, a couple from Howe and most from Gary Coleman's thesis, to determine a bunch of these coefficients. Next slide, please. Using this, we were able to use a couple commercial planes to help prove our systems weight and a couple other things. Next slide. And with this, we were able to get these, as seen over here, these weight values and coefficients for each of the configurations.
Yeah, zero.
Oh, and now we go into the cost, right? The last thing cost wants to do, the last thing to do in parametric sizing is to determine the cost per plane. One, to help synthesis, give a recommendation for what would be the best design point. To do this, we use Roscom's methodology to determine RDTE and manufacturing cost to determine an overall price per plane. Next slide, please. Doing this, you can see over here, we were able to verify this using both Concorde and Boom Overture's price based off of their different interviews. Next slide, please. With this, we were able to get our actual price per plane as seen in this table with the 80 packs right here C with its cost breakdown.
The results from sizing become the solution space, with each of these lines representing a specific passenger count, and we have multiple passenger counts listed on here over the entire tau range. Next. So, whenever we overlay them, you can kind of see what the differences are for increasing passenger and what it does to a specific concept. So our vehicle doesn't increase that much in weight, even though passengers increased over more than 200, and then the Overture, the weight increases significantly due to those same passengers applied. So looking, you just saw the space, how massive it is. We need to find the racehorse inside that. So we're filtering that down using the previously mentioned selection criteria. Next. For the Boom Overture, there's actually two different selections we looked at. So the selection criteria just mentioned. And then there's also a selection that would be equivalent to what Boom selected for their original design. So we have two examples right here. Next. How do we know these values are right? We need to verify them, and to do that, we need to create a model of what the current Overture is so that we can match it with our size vehicle. To do that, we need planform area, tau, and takeoff gross weight. We get planform and volume from OpenVSP, and then the takeoff gross weight is found from regressions based on similar vehicles. Next. From those vehicles, we have a high technology and a low technology model, one having nothing, and we assume that the Overture wouldn't be at those maximums, so we average it and compare that to the values we got, and the error on the right side in yellow, extremely low, but there is the value of uncertainty, and that's just due to the averaging. Next. Now we have the Boom. We just finished the Boom Overture. Now we're moving to the OAW. How are we going to change inputs, analysis, constants, so that we can get to the OAW? We have a couple different revised analysis, a couple that just require inputs, changes in constants, some significant changes in constants, the structural index and the void volume. So looking over here, typical tail left and what the Overture is versus ours, and the weight distribution is balanced out by the lift distribution, so the stresses are a lot lower and there's a lot more area overall, so we would assume that the structural index would reduce. Next. After we got our initial inputs out, we had this thing. Not good. Anybody that looks at that knows that you're going to have to increase the planform area. So what are the next steps? We look to increase the planform area, but also not increase the weight too much. We found that the void volume coefficient would be able to do that. So at lower passenger counts, we would have that at a high value. And as you move up in passenger counts, you would slowly decrease that. And that's depicted in this model, just how much empty volume versus total volume there is. Next. So that model also gives an example for there's a minimum size vehicle. Say for if you had 1 passenger going up to 80 passengers, those vehicles are going to be pretty similar just because you have to have a minimum size. Changing our selection based on that for the lower passenger counts, just because they wouldn't meet those platform requirements, we had to force select points on there and then went back to the normal selection after 280 passengers. So our selections are 80 and 300 passengers. Next. Why select 80 packs? Well, we had to. It really wasn't good for our design. And it creates the accurate comparison with the Oger. And the 300 passenger, we also talked to the other team. They didn't want to go past 300, but more of our ideal passenger counts would be a little bit higher. The oblique all-wing benefits as you increase in passengers. Next. So verifying that is kind of difficult. There's not much literature, but one of the vehicles that we can look at is the Vanderbilt OEW design. Now, a lot of methods were derived from this and compared to this, so it's kind of hard to take a full error from that. Alright, so instead, all it verifies is the process from inputs to outputs. So we know that that works 100% by verifying it against the Vanderbilt index.
So
Wait. On the race balls.
Yes.
You wear your helmet. Okay, now you can go.
Okay. Now that we're safe. So as we finish up sizing, we take those budgets Jared just talked about and we begin to distribute them across the vehicle. Now how this typically looks is you have the 5 components essential to any airplane: fuselage, wing, tail, engine, and landing gear. Except it's not any airplane. Ours, as you can see, is just the wing. So we ask ourselves, how do we modify the standardized process for unconventional configurations? Instead of thinking about 5 essential aspects, we can think about how 5 essential generators are wrapped up inside one volume. That's volume, your thrust generation, your landing equipment, your civilian control generation, and your lift generation. Thinking in this way is advantageous because it supports a seamless integration of all these components, like I said, into the same volume.
This is just a general overview of the process that we use to lay the vehicle out. In total, our goal as the geometry discipline is to design the vehicle so that it can fit the necessary components, fit the payload, and fly the mission, but also we don't want to paint any of the other disciplines into a corner with the selections that we make early on. So when we do that is we define a parametric model with the lifting surface and plan form. Then we step down. Next, we've got to select just a general family of airfoils. That's to hold passenger count, so we select a supercritical family of airfoils. You have a large, longer section where we can put a feasible cabin while still minimizing the chord length. So we lay the cabin out to the airfoil selection. Then we have to integrate the other remaining hard component volumes, landing gear, and propulsion systems. Once that's done, we can kind of take a look at the wing design, see if we need to add any twists, anything like that. Place control surfaces from input from splitting control. Then we lay out the remaining soft volumes, the fuel, the cargo, any other volumes that are a little bit malleable that we can sort of fit where they go. Perform a round of area ruling. And each one of these steps we're going to summarize, we're going to go into a little more detail in the slides following this.
In the layout, compliance is revisited. We look at more possible mistakes that could be made laying things out. These are more focused on OAW, the max span, again, now seating and emergency exits for the cabin. The supersonic, because supersonic, and the noise limitations. Next.
Okay, so the outer moldline layout is the first real stage of the layout that begins to look like an actual flight vehicle. The thing about it that's challenging is as this configuration changes its orientation and flow, the performance of each part of the vehicle essentially changes. Here, unslued, or at a slight slew, it's basically just a wing. Now there's no fuselage or anything else, but once it's in supersonic flight, it's angled at about 70 degrees, this wingtip becomes effectively the forebody of the vehicle. So its job is to break the flow, throws a Mach cone that the rest of the vehicle can kind of tuck into. So we have to shape the vehicle to make sure that it can remain within that Mach cone the whole time, and then we don't get too much trailing edge drag coming off the back of it. So to do that, we take a planform area, the sizing results to us. Through that planform area, define a minimum and maximum span and aspect ratio. Then we lay the cabin out inside of it. On the right, you can see just sort of the process that we do step by step just to draft that first line. And up here, you can see how the planform area actually comes out based on the size planform area that we get.
From that outer mold line, we're completely limited by the airfoil and the height of how tall we want the cabin. So fitting the cabin inside, first we need to develop how big is the cabin actually going to be. We did that using NASA Flop's cabin sizing and then some values from Roscom. Next. Iterating over rows and pretty much just laying these sections out into 3 seats abreast, which is like aisle, 1, 2, 3 seats. And you can only be 3 seats away from the aisle. That's safety regulations. And iterating through multiple combinations to then determine the minimum volume, maximum revenue, and the mid-range between both of those. We also had a couple different layouts, so one being condensed, one being kind of expanded. So who wants like, you want more economy passengers or you want more luxury experience, then you can add stuff like bars. And next. Verification of this, first it's laid out, and then sanity check, tolerances. If it's failing, you have to return it back to the layout. Next is the Vandervelden. Oh, yeah, that's good. These are the layouts we ended up with. We have our 300 packs on top, 80 packs on the bottom. The 80 packs was pretty tight. So the floor just being flat, it is going to have to curve a little bit. This model didn't curve with the floor, but it's not going to be able to be flat. We also didn't account for the angle at cruise attack, so the seats either have to be inclined or they're just going to have to walk up slowly.
So for the propulsion configuration layout, we have the engine inlet sizing and engine sizing component of the analysis, and how this would be done would be that we take inputs from trajectory performance and from the mission requirements to determine the optimum angle here for the conical spike that would be required for cruise. And so next slide. And so we do that by doing the MATLAB program where we calculated the shock relations from the conical spike to the normal shock that propagates and so on. And so we developed the conical spike angle here, where the verification would come from the Anderson book for shock relations. Next slide. And so our result will be shown here by Andy.
So one of the main goals of propulsion is to determine how big our engine is, right? And one of the ways that we can do that, we can actually calculate the diameter of the engine, right? So this is important because determining how big the engine is going to determine the performance of the engine. In turn, that is also going to affect like how noisy the aircraft is. It's also going to determine how big the nacelle is, so that is going to go into nacelle drag for aerodynamics. That is also going to go into how heavy the engine is, so that is also going to be for weights and balances to determine how heavy that nacelle actually is. So in terms of results, so we compared our results to the known diameter of the Symphony engine, which is 1.83 meters. Our calculated value is 1.75, which is within 4.58% error, so it's pretty good. And then our nacelle has a surface area of 37.0 centimeters squared, and this is actually going to be an input for weights and balances to whenever they do their flops analysis to estimate
the weight of the aircraft.
So to piggyback off of that, the propulsion integration for geometry would need to be a multidisciplinary integration that incorporates inclines, weights and balances, and the propulsion discipline in order to determine the span-wise and chord-wise placement of the pivot structure that the engine would be pivoting about during slew condition, cruise condition, things like that. So for that, they would need to be placed in such a way that they are a function of the span-wise distance of the cabin span, as there's a compliance regulation where it needs to be such distance from that, as well as for weights and balances, the chord-wise placement forwardmost of 20% to allocate for the accurate CG location that weights and balances would need to determine. And that's the geometry there. And this is the analysis, the verification being the literature search we conducted on other OAW vehicles, and the results we passed to the propulsion and aerodynamics disciplines for aerodynamic interference and things like that. Slide.
All right, so what other hard volumes to assess during this configuration layout is the landing gear, and this is designed with the intent of like supporting and protecting the aircraft while it's on the ground and during certain flight phases, especially takeoff and landing. And this image I think could completely encapsulate it, because this aircraft is not landing straight, so it has some yaw, and you can see that one side is higher than the other for the engine, so it's going to have some rolls. So these are very important things to take into consideration. And so this process can be summed up briefly by just like figuring out where the struts are going to go on the aircraft. So, and I say longitudinal, so it means to just take the aircraft on its side and just start somewhat fiddling around with it. But also like having some constraints such as tip back and roll angle, which I will show in the next slide. And from there we figure out a weight distribution for the aircraft, and this will largely depend on the type of aircraft. And from there we assess the ground loads and a dynamic load for these struts as well, and then from there we can find the right tires and just the right size for the struts. And for verification, I do have some list of aircraft that are like similar in terms of like mission or shape or landing gear layout. Next. And so these are the initial results that were obtained for this phase. And these results are obviously very important to figure out like an initial volume estimate to incorporate into the overall design. And you can see here that like these angles, there should be around 15, but they're kind of both on the high side. And this is a very delicate trade-off, because you want the aircraft to be able to have enough clearance to be able to rotate, lest they get yelled at by stability and control for not giving a large moment arm for them to lift. But also like not so that it tips over while it's on the ground. And these results are based on no slew upon landing. And here I just have some dots to mark the landing gear. But if we were to redesign to incorporate slew, one side of the aircraft would have to have a main landing gear in order for two struts to land on, because we don't want to land with one. So this is just for the initial results, and more refinement will be later on.
So we have selected control effectors in the PI phase. So now our focus is to size them. Here's just some literature that we've looked at. Next slide. This is just a rundown of our analysis. We basically used image measurement to get these sizes. So this method has also been verified with statistical process control. It has proven that our method is accurate and repeatable. Next slide. This is just a rundown of our process. Next slide. And so once again, those are the sizes, and then that's the layout of our control vectors. Next slide.
Another goal of the weights and balance team in the configuration layer is to determine the component weights. And in this, we mainly apply the FLOPS method for hybrid wing body, in which we apply different inputs from the different disciplines, but the main ones being type of gross weight and the number of passengers, as well as the surface sizes, for example, for the control surfaces, as well as range and maximum velocity of flight entropy. In here, the method was verified using several supersonic vehicles, including the Concorde and Tupolev, but the main one here being the YB-49 that has almost a similar configuration to what we have, so an error of 13.77%. And these are the results that were generated from it, grouped by the different risk groups with the structure weight group, propulsion systems and equipment weight. Next slide. And one drawback about this method is it's a development from empirical and historical data, and so it may overestimate or underestimate some component weights, but that is accommodated in the configuration layer first by distributing those weights within the different weight components that can be moved around in the configuration.
Now that we know all of the weight components, we can now start to determine a CG by placing these different soft volumes and hard volumes. We're trying to aim for around 32% of accord based off of different conceptual design papers saying that produced stability, or that made that CG kept the thing stable. So that's what we're that's what we're trying to aim for. Next slide, please. To do this, we use OpenVSP to help model the aircraft to put all these volumes together, and we proved it using an X59 from last semester. We had an accurate model. That was the biggest concern, was the model. Anyway. So, as you can see here, for our 380 packs, that red dot, as seen here, is the actual CG location. For the 80 packs, we were able to get close to that 32% of the chord, around 34%, but the 300 pack was about 10% off. We can still mess around with some of these soft volumes, including the fuel volume, cargo, different types of things, but that still needs to be played around.
Okay, so air drilling is a process in which you're attempting to minimize the wave drag the vehicle creates for itself as it travels through flows supersonically. To do that, you basically evaluate the cross-sectional area of the vehicle to match the volume distribution to the known shapes for the ideal volume distribution in supersonic flow. So what we find with this configuration, if you can go to the next slide, this is the process, but the results here show us that this configuration type lends itself extremely well to air drilling for minimizing wave drag. On these plots you can see the blue line represents a Sears hack body, which for a given length and volume is the ideal shape for the minimized wave drag, and the other lines are our vehicles after the full layout has been performed. You can see they match very well. The small humps that you can see in those plots essentially relate to the engines and vertical tails. And then this is a summary of the vehicles after layout, their platform areas, their towels and their KWs on the left-hand side with the 80-passenger version, and the right-hand side with the 300 packs version.
So I'm gonna go through this a little fast because we're coming a little short on time here. When we move to the evaluation phase, we ask ourselves, did we make the right choices during the layout and sizing phase? Depending on how unfeasible you are, you kind of ask yourself, do I need to go back inside a different concept, or can I just alter the design? We're analyzing feasibility. Now, feasibility involves two parts, physical and economic. Physical is just meeting the performance requirements, and you can do that, but nobody will buy your ticket. So it's also important to be economically feasible because both serve to limit your product's operation. Now, the first step in deriving the methodology for this phase is to determine the most important considerations in each phase, as we've done here, with just a little representation. Really, takeoff and landing are the most dangerous because most aircraft accidents happen during this phase due to things like engine failure and stability and control concerns.
So, for aerodynamics, this means we are up first on the docket here to determine the performance of the aircraft. With this little reduced order model right here, our lift generating components are mainly going to be in our big wing. And all of our drag components are going to be in the nacelle, the wing itself, the vertical tails, and then our control effectors as well. And so, using verification data from wind tunnel testing data from various wind tunnel models, we then go into our method here. We use VLM, next slide. We use vortex lattice method in VSP Aero's vortex lattice method software to determine both the lift, drag, and all the force and moment coefficients necessary for force and moment coefficients that are acting on the aircraft at any given point in flight. And we also take OpenVSP's parasite drag and wave drag tools to generate a full drag buildup of the vehicle. Next slide. So this is some of our verification data. As you can tell with this variable speed model right here, we had some issues due to modeling. And so this means that as we go through the process and we go back through CL, we need to make sure that our models are accurate, or else we will get some very interesting results, which we'll see on the next slide right here. You get some wake separation right there. That means that the model has failed. And so going forward, we need some models that look more like this right here. Next slide. Going into our subsonic performance right here. For our takeoff at 80 packs and 300 packs. The 300 packs very much wins out with a 27.9 versus a 23.3 at zero salute. For subsonic climb, we have a max LFD of 29.5 with a 300 pack solution, and our 80 pack solution goes down to about 24.7. Now another thing to note here, for subsonic performance, our salute angle decreases our performance, so it is necessary to limit the amount of salute that we have at low subsonic performance, or low subsonic speeds in order to, next slide. For supersonic performance, our LFD is pretty low for both subsonic climb and for supersonic climb and supersonic cruise. And what this indicates is that we need to go through a major redesign of our wing. But what we can tell is that for our supersonic cruise, our max LFD matches our Overture's max LFD of 5.8 using vortex lattice. Next slide. And then this is our landing results as well. We have a 27.9 max LFD for our 300 packs, and then for 80 packs it is a 23.3. Next slide. Overall conclusions that we can get from this. We can make two major design changes that will occur in parametric sizing as we reiterate the vehicle. One, by increasing the aspect ratio of our vehicle through reducing the induced drag and wave drag to cruise. And then another thing we can do is we can change our airflow to have a lower design lift coefficient, so that way we can operate at lower angles of attack more efficiently. Next slide.
So for figure eight evaluation for propulsion, we use the elements of propulsion book to do the engine performance analysis, and this is the verification that we would do, and the methodology is laid out here. So the verification software, Mattingly's PERF software, would be utilized to verify the thrust output and specific fuel consumption that we get for each altitude and each Mach number, and the conclusion. And here's the results here for cruise, takeoff, and landing. Next slide, please.
So now our focus is to visualize different critical conditions along the flight mission profile. Next slide. So these critical, so this is just our method. Next slide, please. Next slide. So our results are that we have no trim solution. In other words, we have no adequate control power. So that means that we have to go and resize back to CL. That means either resizing or to place the control flexors in a different position. Next slide. This is just our method to climb. Next slide. Same for cruise. Next slide. So landing also has shown that we need to go back and resize and reposition the control flexors. Next slide.
As far as performance goes, taking a look at the takeoff performance, this does a really good job of showcasing just how much of a multidisciplinary balance it is. Because you have the physical limitations that you are limited by. You have a finite amount of runway, and a finite amount of thrust, and what you can do. Next slide. The method is based off of one of the methods Roskin has provided, and for using the Concord as a representation, it is under 3% for production takeoff length required. Next slide. As far as the results go, unsurprisingly, a lifting body is an absolute stallion in generating lift, so slew wall. That significantly decreases, however, as your slewing wall is increasing. And there's two compounding factors for that. One, you're just losing lift because of the speed. But the other is that your geometry constraints become more stringent because your striking angle is reduced lower and lower. Next slide.
So we reviewed the tree analysis that we did in parametric sizing that was verified with the 9% comfort data. And next slide. So these are results of the 380 pack configurations. 80 packs can meet all flight phases with this current thrust. Our 300 packs cannot meet any of the supersonic flight phases with this current thrust.
Well, another important analysis to conduct is the range analysis that determines whether we can achieve our design range, which is 4,250 miles, and as well meeting the requirements. Next slide, and this will be applying brigade range. So please. The method was verified using Concord data with an error of less than 10%, that is 7.96%. And here are the results for the 300 passenger and the 300 for the landing weight and the maximum range for the 300 passenger configuration. And you find that at an optimal LOD of 8.29 at cruise, we get a maximum range of 5,658, which is well above the 4,250 design range, and aircraft meets the range requirement. On to landing analysis, which is another important parameter that FRR pays attention to. And this requires that our calculated distance be able to account for, be able to have enough distance to run within the available landing distance. Next slide, please. And with this, the method was verified using Concord data to 6.47% error. And here are results with the 300 passenger configuration, and you find that the configuration is able to land safely for the 3 of the 4 available runways, that is 2 at MHR and 1 at JFK, so we made minimum FIR requirements for configuration.
So further expanding upon the landing gear, we also evaluate the forces on this landing, and also just evaluate some additional features of the landing interface for slide. And this will just begin with just laterally placing it, while also creating roll clearance, and as well as just finding the landing gear, and the roads can be determined from there. Next slide. And so here, if you kind of just look closer at the results, you'll see that these are extraordinarily high, and these assume the worst of the worst landing at gross takeoff. So basically immediately taking off and then coming back. But I'm pretty sure that, or more than likely that there are aircraft features and proper landing gear design can take care of this. And so these, this is also assumed with no slew. If it were to be with some slew, it would be redesigned as well.
On the structural analysis, on here we just evaluate the aircraft structure to make sure that it can perform even the aircraft performance. Next slide, please. And to do this, we start with the VN diagram, and this here just explains the limits that the VN diagram describes, and it being verified with Concord data. Next slide, please. And here are results for the both configurations with a maximum load factor of 3.7 and 2.91, which clearly meets the FI requirements of 3.8 for passenger comfort and safety of the aircraft. And using that to evaluate the structure of the aircraft, we find that the maximum load on the aircraft, I guess the weight generates a load factor of 2, so it's a 1.5 factor safety getting to the factor, an ultimate load factor of 3.0, which is well within the Venn diagram, and the aircraft can be approved to fly with the structural limitations.
Now we go to how much would it take to actually go through and fly this mission, and what kind of maintenance expected to do. To do this, we're actually going to be using Roscom's operational cost.
So I have to preface our cost analysis here with the fact that we had some internal issues that kept us from providing cost output, unfortunately. I just wanted to send a shout out or bring Mr. Lynn and Settles on the other team for letting us commandeer his operational and maintenance cost code to determine the vehicle price and the ticket price. So Prince, if you'll take it away with those results, please. Or yeah, thanks to.
The results are essentially what we would expect from how the internal geometry configuration. The 80 passenger variation is not very favorable from a price standpoint, from a ticket standpoint, as compared to the 300 passenger variant. And that's just because largely due to how much room is being wasted versus used. And the comparison points for this are current costs for same transline flight, as well as the today's equivalent price for the Concord record.
So, just some conclusions to wrap here, and I'll make this quick because we're a little over time. So, when we look at the 300 versus 80 packs, we learned something very interesting. When we started the project, we thought 300 would be the winner all across the board. That's true from an economic perspective, which makes sense. The more people you can pack in a volume, the more you can charge them. Also, the operational cost between the two vehicles didn't differ much, so the economic advantage is clear. However, and then the 80 packs can't fly the mission. Yeah, sorry, I'm getting mixed up. 300 can't fly the mission, the 80 can fly the mission. So then we learned with Lincoln's cost analysis that the 80 packs has a pretty bad ticket price that we went over. So it's the trade-off between performance and economics that we really learned throughout this project. We do have some incomplete results. We need to further refine our error data and methods. Also, we need to do the same for stability and control. Everything's dictated by slewing configurations, so we need to analyze that in the future. You could also do some mission profile traits. We assume the mission profile was static for the entirety of the analysis, which in reality, if we were operating on our own parameters, we could analyze those trade-offs, but for now, we did what we provided at that range. The future field of development that we didn't discuss in this presentation would be military. The literature itself is producing some military variants, although not many details are available, and local technology. This is a hot button item right now. It is very expensive, but it does have promising results. Citation.